Hello everyone, this is Mr. Lee. In this video, we are going to go over the forced body diagrams or the free body diagrams, but this time we're going to go into angled surfaces. All right, let's begin. So let's come up with the scenario first. Let's say we have a book, right? So we have a book on a table. So let's first sketch out this book on a table. So this will be scenario one. We have a book on a table. Book on a table. So this is something that we've done before. Okay, so let's just do a quick free body diagram to see how the original book on the table changes when you change the angle of the surface. So if I were to do a book on the table, and if I were to do like an interaction diagram, right, I can say we have a book, right, and that book is interacting with the earth, right, because we have the force of gravity, and there's the table slash surface, right. So these interaction diagrams, you'll come to realize that these are very helpful. These help out a lot when you come up with your free body diagrams because basically it tells you all the forces necessary. So the book on the table, right, they interact with each other. So I'm going to draw two arrowheads like this, and the table on the surface, they interact with each other. So we're going to draw two arrows like this. And we can say that the earth exerts a force on the book, right? Earth on book using the agent-object notation, okay? Or we could just call this the force of gravity, or we can also call this the weight, right? So there's three different ways to write it until we feel a bit more comfortable with the notation. Let's stick with FE on book. And also we have the book on the surface. So if you remember, this is the normal force. So the normal force of the surface on the book. All right, so here we have our two forces there. And the reason why these interaction diagrams really help is because it shows us exactly how many forces we need to draw. The first one, of course, always being the force of gravity, or the force of the earth on the book. And then we have the normal force, or the surface force, okay? Remember, quick tips, right? Always make the normal force, okay, have it be 90 degrees there as a reminder that normal simply means 90 degrees with the surface. All right, so now that we have our two forces, we are going to first identify that the acceleration is 0 meters per second squared, right? That just means it's not speeding up or slowing down. And also, we can say that the velocity is 0 meters per second. These are not necessary for free body diagrams, but it sure does help, doesn't it, to help you remember exactly what's happening here. All right, now because of this clause right there, this clause means that all of our forces have to have a equal but opposite component. So here, the weight, or the force of gravity, or the force of the earth on the book, is equal to this normal force, or the surface force on the book. Okay, so that is the link here. You know what? That's so important. Let's write this down here. This means that all forces must have an equivalent but opposite force. Okay, that's what that means. Very important. Highlight that key part to this entire unit. And the reason why I want you to have that is this won't always be the case where your acceleration is not 0, where an object is in fact speeding up. Okay, so this here helps us keep things nice and organized. All right, very important there. Start that. All right, so we have a book on the table, and now let's see what happens when you adjust that book on a table. All right, so here on the screen in front of you, you should see a simulation by the physicsaviary.com. I'll put a link in the show description so that you can explore this yourself. But this is our book on the table, right? So we can see here, they also did the equal forces method by showing the size of the force. So the y-axis, this red vertical force, is 10 newtons tall. And so that must mean that this force of gravity down here, the blue one, is also 10, but negative direction. So what I want you to see is this is a flat surface here. There's two things I want you to focus on. One, you see the y-x vertical axis that they draw, right? See what happens to that y-x axis with respect to the surface, or the surface of the table. And also, try to see what happens with the two forces that you see in front of you, all right? So let's begin. Here we go. Okay, so in the we see that the surface is being angled. Okay, Right now it's around 20 degrees. There's a couple of things that you should see here. I'm going to pause this simulation real quick. One thing that you see is that this vertical or the normal force is shrinking, right? It used to be at 10, but now it's no longer at 10. Okay, it shrunk a little bit. The force of gravity here, it's kind of hard to see, but I'm going to tell you this. The force of gravity for this object, or the weight of the object, that never changes. Okay, that arrow size is the same length. And the other thing I want you to realize is the y and the x-axis. Notice how the y and the x-axis shifts along with the inclined surface, and that is key. That will really help us moving on. Now, the other thing that I want to show here is the gravity components. All right, so see what happens as the gravity components, or as the incline increases. So as you see here, we can see that the gravity components are actually shifting with the incline. And that is a very important idea that we will work with here. All right. Another thing that I want you to realize, we'll put this up when we reach the bottom, is that the acceleration for this object is 0. Not because it's not moving, but because it's not speeding up or slowing down. Remember, that's the definition of acceleration. But there are a couple of forces here that I purposefully hid so that you didn't see it in action. But if I were to ask you, right, if you were to increase the incline of a surface like that, what's going to prevent the book from sliding down? And hopefully you can answer, oh, the force of friction. So I'm going to activate the force of friction here so that you can see what's happening as this book is increased on the incline. So the surface, as the incline is increasing, we see that the force of friction vector is also increasing, right? So that kind of makes sense. When you increase the inclined angle like that, the book wants to slide down, but the force of friction is going to prevent it from sliding down. Now here's my challenge to you. We know that the acceleration is 0 for this, and right before we went to the simulation, I told you all of your forces have to have an equivalent force, basically to cancel it out. So see which force is canceling out the force of friction. So we see that the force of friction has a rightward component to it and is increasing. So see what component is also increasing to cancel it out. And if you said it's the force of gravity, one of the force of gravity components, you'd be correct, right? It's the one that is parallel to the surface. And we can see that as the incline decreases, that component also decreases with it. All right. So I'm going to let this run for a little bit until we reach the bottom, and then we'll go straight back to our notes. There we go. So we're back. Let's give ourselves a couple of rules for drawing objects on an incline. So the first rule is establish the y-x coordinate. Okay, so what that simply means is make sure you know what is vertical and what is horizontal, right? And let's do a quick little example here. So if we had a object on a surface, so a flat surface, object on a surface, I can easily say that this vertical axis here, this is my y-axis or my vertical axis, okay? And this axis here, this is my horizontal axis or my x-axis. So here, with this orientation that we're used to, this is where our rules come into place. This horizontal axis, right, it must be parallel to the surface, okay? And with this y-axis here, let's do blue, this y-axis, I'll recolor it in so that we have different colors. It must be normal / perpendicular to the surface, right? Or at least the x-axis. So with these rules into place, let's figure out how we can draw the xy coordinate plane. I'll just do it right here. So those are the two rules. I'm going to draw the surface like we saw on the simulation. Right? I'm going to draw that. I'm also going to actually let's do that first. All right. Sometimes I'll draw like a ram, so I'll draw like a triangle, but for the sake of this video, I'm gonna skip the triangle part. All right, so here we have the object on the surface, like this right here. Okay, so rule 1, the x-axis must be parallel to the surface. So until we get used to it, I encourage you to draw the horizontal axis right on the object itself. Right, so this is our horizontal axis, and the y-axis, it must be normal or perpendicular to the surface. All right, now these are the rules that you should follow, and it really does help when we are drawing our force body diagrams and labeling our forces there. All right, so those are our 2 axes. What I like to do in the corner is I also like to indicate my axis. Okay, and this helps when you are not drawing the axis directly on the object. Okay, so that's our y and our x. We are going to say that our velocity is 0 meters per second, and our acceleration is also 0 meters per second squared, right? It's just a good reminder for future sakes. All right, so that's rule 1. We did it. Okay, we established our axis. Rule 2. A lot of the times our objects will always have some kind of mass, and it will always have some kind of weight. And we call that weight the force of gravity, or the F of Earth on the object. Okay, I'm going to make this nice and big because this is very important. Always points down. Our force of gravity always points down. I'll do my force of gravity in black. There we go. So from the object, I'm going to go straight down, just like that. Okay, so we're going to label this F of Earth on book. All right, straight down. All right, now the next part, I'll explain the math behind it, but I want to show you the rule first. Okay, so the third rule is angle of surface always touches the object. So what I mean by that, I'll draw the angle of the surface in a different color so you can easily see this. Let's do this in purple. Yeah. So let's say right here, this angle, that's not purple, that's red. There we go. This angle, let's call this theta. Okay. So the angle of the surface, we call theta, and the units for this are always degrees, not radians. So if you're coming from math class, be careful. And that angle is the angle right here. So notice how this angle is as close to the object as possible. And that's what I mean by the angle of the surface is always touches the object. But if we were to get like really technical here, the angle is made between the force of the Earth and the y-axis. Okay, always, 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 unless they give you some other angle, and then it'll be something else. All right, so that's our angle right there. Okay, if the angle of the surface is theta, the angle between the force of gravity and the vertical component is theta as well. They're the 2 same angles. All right, and the very last thing that we need to do is, so this is step 4, we have to create force components to angled forces. Okay, we need to create force components to angled forces. And what I mean by components, this is a f of x, or a horizontal component, and a f of y, which is a vertical component. Okay, now it's important to know that your force components are not actual forces. Your force components make up your force, but they're not the forces themselves. And we'll go into how we can determine those as well. All right, but let's just finish this sketch here for the sake of completion. So we have the force of the Earth right there. Let's do the normal force as well. We'll just do this in black. Okay, we have the normal force and it's perpendicular to the surface. Also, realize that the normal force on the book, it lines up with your vertical axis. Okay, and because your vertical axis is perpendicular to the surface, and the very last force will be that force of friction, and we'll draw it like so. Okay, the force of friction on the book. So that is our free body diagram. So if you ever have a FRQ or a problem that asks for a free body diagram, that's what you need to submit. Okay. I guess let's do a quick little sketch of what you need to submit, because all of that's not really important. All right. Boom and boom. So this right there. Okay. You only want forces on your free body diagram. That's what you need to submit. Now, what I'm about to show you are the things that you should do in order to help you out when you're solving the problems. And that includes the force component. So let's go into the math of these force components, right? These vertical and these horizontal axes. So if I were to just focus on the force of gravity, right? So we have our y-axis like this, and we have our x-axis like this. I'm just focusing on the force of gravity component. I'm going to draw it nice and big, okay? And so should you on your papers. So we have the force of the earth, or the force of gravity, right there. For the sake of this video, I'm just going to put F of G because it's just a little bit quicker to write. All right. Now, because the x and the y axis are not along this force of gravity, and so what I mean by that is if you take a look at this force of gravity here, okay, this force of gravity that I'm highlighting, it's not along the x or the y, right? But if you compare this to, let's say, the normal force, we'll do the normal force in blue, this normal force, you see how it's along this y-axis, right? So that's along the y-axis. And let's look at the force of friction. So this force of friction here, you see how that's along the x-axis, right? That's how we know we don't have to come up with the force components. But this force of gravity, which I highlighted in yellow, is not along either the x or the y axis. Therefore, we need to break it up into its x and y components for the sake of us being able to do the math. All right, so when you come up with the force components, okay, so we have our, right, so that's our y-axis and this is our x-axis. All right, it's important to first identify, so this is theta, this is also theta here. To label the x and y axis, we just simply use name of the force, so the force of gravity, and the axis that it's along. So this will be called FGY. I didn't draw it yet, so I'm going to draw it right now. Let's do FGY in red. So this is FGY in red. Now it's important for notation's sake, because these are not actual forces, that you use dotted lines. Okay? The dotted lines tell us that these are not real forces, but things that make up the forces. So that red dotted line is what we call FGY. Now, if you're pretty good at this and you're used to knowing that it's not a real force, you can draw a solid line, but that's fine. All right, and next thing is FGX. So FGX we'll do in let's do green. FGX. See how I draw this? My arrowhead first. Okay, along here. This is FGX. Let's label that. FGX. So each of these components is describing something for our book. So FGY means the force of the earth pulls the book against the surface. Okay, we don't want to say it pulls it down because that's what FG does. So let's just write that there. FG pulls object down. Now here our verbals are very important. FG pulls, or the force of the earth always pulls objects straight downwards, but FGY is the force of the earth and it pulls the book against the surface. And we can say FGX is the force of the earth in our diagram here, pulls the book to the left. Okay, I'm going to put it in parentheses, the left of the x-axis. And we know that because of this arrowhead. Now this is a part right here that a lot of students mess up. So I'm going to put a little star right there. Okay, a lot of students don't put the arrowheads appropriately where they belong. So a good thing to do is, of course, the verbalization. Right? What is this FGX doing? And it's pulling this object to the left of that surface. What is this FGY doing? Well, FGY will always be pulling this object against the surface. So those arrowheads help us out here. And what I mean by a lot of students mess this up with the sign of the arrows, when we get into the mathematical portion of it, the direction of the arrows are very important because anything to the left is negative and anything down is also negative. Okay. All right. So that's what f of g y and f of g x means. And if we were to continue our definition of f of g, right, for this situation, we can say not only does the force of gravity pull the object down, okay, with respect to our scenario, it pulls it down against the surface and down the ramp, or I guess to the left of the ramp, right? Down and to the left of the ramp. So against the surface, this is describing, I used red for this, right? So against the surface, this is FGY, and down the ramp, we use green for this one. Down the ramp, this is FGX. So we can see that within our verbalization, right, F of G pulls the object down against the surface and down the ramp. Within our verbal, there lies our FGY and our FGX. Great. Now, here's the tricky part. Let's go into the trig portion of these angled stuff. Right? So I'm going to leave that there. I'm going to do my trig stuff on the side. So here's something that you should know. Right? You might have seen this before. So sine of theta is opposite over hypotenuse. You might hear me call this so, right? And then we have the cosine of theta, which is adjacent over the hypotenuse. You might hear me call this ka. And then we have the tangent of the angle, which is opposite against the adjacent. So that's TOA, right? So I'm going to highlight. So we have SOH, sine, opposite, hypotenuse. We have ka, which is cosine, adjacent, hypotenuse. And we have TOA. Let's do TOA below, which is the tangent, opposite, adjacent. So we have so, ka, TOA. So, TOA. There we go. All right. Now, in terms of math, what SOHCAHTOA, or what these trig functions tell us, is just all these are what we call ratios. Okay, that's all there are. So like a 2 to 1 or a 3 to 2, right? These are all just ratios. So what this means is that for sine, the length of the opposite side and over the length of the hypotenuse will always give us a ratio that is the sine of theta. So for example, if our sine of theta gives us 1 over 2, okay, so that's our ratio. And let's say we have, because we're doing sine, we have an opposite length of, let's say, 24 meters. Our hypotenuse length must be 48 meters. Okay, because the sine of the angle, which is 1/2, always has to give us a ratio of 1 to 2. So that's what sine, cosine, and tangent, the SOHCAHTOAs, it just simply means a ratio. So in terms of physics and in terms of this, it's important to know how to find these ratios. Right? So if we take a look at FG1Y, you see how this red side is touching this angle? Because it's touching the angle, we call that the cosine of it. All right, so let's put this over here. We can say that FGY, okay, we have to use a cosine. And because we know that FG is the hypotenuse, we can say f of g y over f of g. FGY is the adjacent side, is equal to cosine of theta. For our drawing here, we see that FGX is opposite of that angle, right? It is as far away from that angle as possible. We call that FGX over f of g is equal to the sine of theta, right? So this gives us the ratios for our sides, just in case we need to find FGY and find FGX. So we have to set up our ratios like so, and we can simply use algebraic manipulation to come up with our missing side. So if I were to go over, a little too far, over here, we can also rewrite this, okay? If I remove FG from the denominator, we get FGY is equal to f of g cosine of theta. And if we also get rid of the denominator for the sine of theta, we can get FGX is equal to FG sine of theta, right? So we can find the unknown side by the algebraic manipulation there. And what this usually means is you are usually given f of g, okay? Or you can find f of g. So basically, you're given the weight of the object, or you can usually find the weight of the object, because most problems give you the mass. Okay, most problems give you the mass of the object, and with the mass of the object, we can find f of g. Here's our first formula, given m times g. Right, so the mass times the acceleration due to gravity, and we can say that the acceleration due to gravity is going to be negative 10 meters per second squared, or actually not negative 10 meters per second squared down. There we go. And that, if it's down, we usually write negative there. So let's highlight that. Very first formula for this entire unit. Boom, right there. And we'll do a lab to see this ratio here in class as well. Alrighty, cool. Also it's important to know that weight, or f of g, does not equal mass. Alright, so let's use red. So red star. Red star means very important. Stop. Halt. Okay. A place to make a mistake. Good. Alright. The very last thing I want to brush up on in this very long video is this idea where your acceleration was equal to 0, and what that meant. So if I were to come up with a component version of our free body diagram earlier, right? Remember, we have f of n, we have f of g, okay, and we had f of f. The way it works out, because we said our acceleration is equal to 0 meters per second squared, right? All of the forces have to have something that cancels itself out. So if I take a look, and if I create here, okay, this is my FGY. My FGY has to cancel out something. And the only other force that it could possibly cancel out along this y-axis is f of n, because there's no other forces around. So we can say FGY and f of n, value-wise, are equal to each other for our drawing here. Okay, but FGY, of course, being negative. And we can take a look here for the other force. Here we have FGX, right? So the only other force that's along a horizontal axis or along the surface axis is our f of f, right? So our FGX and our f of f are equal to each other. So because they're different values, so we can say our f of f is equal to our FGX. And this should make sense, right? Because we said that FGY is the force of gravity that pulls the object against the surface, and f of n is your surface force. So the Earth is pulling the object against the surface, and therefore the surface is pushing back by the same amount. And here we have FGX. So FGX, we said, is the force of gravity that's pulling the object down the ramp. And what's going to prevent the downward pull, well, is the force of friction. Okay, so this statement here makes sense. And we just did that by just looking at the free body diagram. When we have more forces, this will get a little bit trickier, but we'll cross that bridge when we get there. Right? And that's that. I hope you took a lot of notes. I'll see you next time. Bye-bye.